Okay. So thanks, Eleni, for the handover. Hi, guys. My name is Giacomo. Thanks for the quick introduction. As Eleni said, I work in the traffic solution department at KISTLER. And today for me is a big pleasure, as was already last year, to try to motivate some of you to cooperate with us and develop a master thesis in a real practical problem. Indeed, today, the speech of today is putting theory in practice with KISTLER, so bridging the gap with SIHM and wake in motion. I think that being students of this class, you know already the topic SIHM. I will explain a little bit better what is wake in motion. Here, if you have the occasion, we have some demo unit for both technologies. Eventually, you can look into it. And yes, the main topic is bridge monitoring. I belong to KISTLER since 2 years. I'm responsible for the global market. Even if the company is settled here in Winterthur, we have so many bridges around the world, in US, Southeast Asia, so I pass mostly of my time in the airport rather than in the office. And it could be a pleasure for me today to show how we integrate this technology and we address the problem of bridge monitoring. Just a couple words about KISTLER. If you know the technology itself, the acceleration sensor, it was invented indeed by Mr. Crystal in the 1950s. What I have here in my hand is a piece of quartz. If basically every employee passed the probation period, they give it to us. It doesn't have big value, but for me it's a good piece of quartz because I don't know if you know how the acceleration sensor works. Basically, Mr. Kistler has the capacity to get a really nice hint from the piezoelectric effect that each piece of quartz has. If you compress, basically the element give you an output in thermal resistance that with a dedicated charge amplifier you can convert. And this measurement you can convert in terms of acceleration, torque, force, and pressure. So you can imagine that this is a good technology to measure everything. And indeed, in our portfolio, we have more than 1,000 different acceleration sensors for different purposes. My business unit, as I told you, is focusing on wake in motion and structural monitoring, but we have also very nice application for aerospace, vehicle testing, automotive. Here, usually when I talk with guys, I tell you that one of much more interesting customer. If one of you has some Nike shoes, I think that is very intuitive to know that we have LeBron James, our customer, because the Nike World headquarters in Oregon basically is a studio where you can test all the... Here it should start the movie. Yes. Basically, in this headquarters, Nike design every training shoes for each purpose. Is running, is track recording, is basketball, and every type of sports. So just to say that acceleration measurements are everywhere. And with our sensor, we try to develop the high cutting technologies for these purposes. Also, we have a sensor in every kind of sports related, even the Olympics, for the starting point of the swimmer, even for the ski, when the skier need to start their race, and so on. We have also some more serious boring application as here in NASA or in China Express sensor. So basically the sensor are used to understand how to fix the tube parting of the shuttle. Yeah, you can switch. No, don't need. Sorry. Thank you. Exactly. And yeah, that's all. So this was just a quick introduction about KISTLER and also the topic of acceleration. Now I will start the presentation more talking about bridge. So anyone is Greek here apart of Eleni? Here? Okay. Yeah, because it's a Greek word. I hope to pronounce it in the correct way, so you eventually can correct me. Hiefirophobia? Cool. So don't spoiler the meaning of the word. Someone who knew, everyone knows that phobia is fear. Yephiro means bridge. So basically is the fear of bridge collapse. I always start this topic talking about this word because unfortunately I think all of us here in the room knows that bridge collapsing is a problem that is affecting all of the world. When I need to approach a customer in Malaysia, in Zimbabwe, everywhere, there is always a quick search on ChatGPT or Google and say, last bridge collapse in that country. There is always. And unfortunately, this is a problem, is a topic that is worldwide diffused. And yes, this is the reason why I can report you a couple of really important bridge that been collapsed recently. I think one of you know Carola Brücke in Dresden. Actually, I was for a conference regarding monitoring bridge in the same period, so perfect timing. Luckily, there was not any fatalities. Also, another collapse in Italy, where actually I come from, collapse in France, in Norway. So it's a problem that is mostly diffused, as well as in Asia and in Africa. So which is the problem? Unfortunately, as a civil engineer, we know that we design something to last much more time possible, but the lifetime at a point, even if it's really extended, is limited. And unfortunately, the big majority of the bridge has been designed 50, 60, 7 years ago, and now they are approaching the end of their lifetime. There are also other causes for the collapse. Designing deficiency, especially in, let me say, poor country or not much more developed as Europe or in US. The designer that doesn't use the perfect assumption, and sometimes even a brand new bridge collapse suddenly. And also the biggest problem that we like to tackle with KISTLER is the overload trucks, because the big majority of the bridges don't been designed for the current traffic load. Imagine that in the last 60 years, the population worldwide doubled. And in this case, also the trade, the cars, the utilities. So it's very difficult to take into account this problem. And unfortunately, this is boosting the degradation process of the bridge. Among the hugest or the most famous collapse, I like to report, unfortunately, a case from my country, Morandi Bridge in Genoa. So here, basically, it was from a media point of view, the trigger of our business from one side, but likely also from the authorities to keep into account this problem more seriously. Especially in Italy, there was a huge investing of money coming from the European Union, which brings, especially to the university, a lot of topic, a lot of people starting to study this problem. Indeed, I was finishing my PhD, and in the last 6-7 months of postdoc, I was responsible for the monitoring bridge around Venice, not those one Masuri, because it's impossible to monitor and they will stand years and years, but those one belong in the mainland. And in that period, the interest for me to tackle these problems arose. And I decided to join in this company. So regarding the Morandi Bridge, the collapse was in 2018, so several years ago. The biggest problem, obviously, was the number of fatalities, which was very resonant. There are some laws that try to understand the value in terms of loss from economical point of view about the fatalities, but for me, this is, my opinion, still unbeatable. You cannot match. If you need to give a cost to the collapse of the bridge, in this case, JP Morgan estimate 500 million. So imagine that to build a bridge big like this, you should take into account 150, 200 million. So the cost is even more, even double. And despite the cost, because you need to spend, I remember I have a friend of mine that worked in that topic in that period for ANAS, which is the biggest road authorities in Italy. Just to demolish the bridge, you need to spend 100 million, and you're just removing what cannot be work anymore. And in terms of disruptive or in terms of inefficiency, the bridge was also belonging the port area. So you can imagine that all the trucks coming through the airport should make an alternative path, and this was a really big pain. Luckily, from this big problem, Italy, we are always best how to resolve to making money from tragedy and try to make some guidelines, as was for COVID, earthquake, and so on. Also, with this case, we start to set new guidelines. So all the asset of bridge is split into region. Not before then, monitor need to be inspected, and after you understand which one is more critical, and you start to monitor. So the Morandi Bridge gives to us a big lesson. Unfortunately, you cannot approach the monitoring, the inspection of the bridge just with a reactive approach. You need to do predictive. So how it works usually. Here I can give you 3 different scenarios, and I will explain you also how much cost in terms of price, because for me it's the most important question. We usually approach a customer, I present all the portfolio, I said my speech, and after, how much does it cost? So here I try to answer to this question very intuitively. As you can see, there are three phases when we design the life of a bridge. There is the designing phase, the construction phase, and you can see in the y-axis the construction phase at its end, but the beginning of the operational one is conditioned at the highest level, so the bridge is brand new. After 100, 150 years, so progressing with the time, in the operation phase, the conditions start to decrease their value. This is pretty intuitive. So in the normal approach, what the operators can do? They do periodic inspection. Every 2-5 years, someone goes on the pitch, does a picture, look with his experience-based approach if there is some crack or if there is humidity. I also did this job for 2 months. Even if I was not paid, it was one of the most boring things that I never did, because you imagine there is not just one span. In one viaduct that could be 30 span, and you do just picture, same one, and you need to analyze manually at home, and sometimes you didn't label perfectly the span, you miss one side with the other one, so they are much more qualitative rather than quantitative. And if the bridge has specific needs, for example, close to a river, or there is an abutment that has a problem of slope stability, you do some extraordinary assessment. In terms of cost, here I report that the building cost is around 100 million, just to give you a quite easy number to remember. And the periodic inspection cost 2 million, while the extraordinary assessment cost 5 million. Okay? So now let's go to the case much more common when suddenly comes up a failure. I located the failure here, so approximately 70-80% of usage. You don't know where it could happen, but it happens. So in this case, you have a collapse, not of the bridge itself, but its condition. And this in terms of cost is around 10 times the cost of the building of the bridge, because you need to put into account fatalities if there are some trucks that is passing on it. You need to put into account traffic disruption, and especially now with social media, if there is a viaduct in the middle of nowhere, someone with TikTok put a picture, the country need to face a huge problem in terms of visibility. So you have two ways how to approach, or with reactive, and in this case what you can do, you can go on the bridge, you say, okay, we need to repair. We need to put something or reinforcing. In terms of cost, this is around from 1 to 10 million. But the important point is not how much I'm spending, it's how much longer is the extension of the lifetime. What I'm really gaining is more or less than 10%. So I'm making the bridge alive, I would say, other 20, 30 years, because at the point, he will need again a major restructuring. It's like just a small spot. What could happen indeed with the proactive approach? For each small green window, you can see that you are continuously monitoring the behavior of the bridge, since there is a moment when the system is going to tell you an alarm, because there is, for example, we'll go a little bit deeper during the lecture, you are monitoring the trend of the frequency. The frequency is correlated to the stiffness. So if there is an anomaly in the first, second, and third bending mode, you can understand that something is going to happen in the bridge. So the system is continuously recording and is giving you an anomaly detection. In that case, the operator, with the support of the bridge engineers, with the support of KISTLER, with the support of Professor Azzi, can tell you, okay, I need to do something. What I can do? I can do an upgrade of the condition of the bridge, basically on three aspects. I can go on the bridge and say immediate inspection what is happening. I can do a partial closing of the bridge, because our aim is not to keep the bridge closed, I need to keep the bridge open. Because otherwise, you will always an alternative path. Some people pass on that bridge because they have only that way. Imagine a city like New York. They have saving connection. If you close one, the 30% of the traffic is spread in the other connection. This makes mass. Or I can do reinforcement. This really small upgrade in terms of cost, because I never quoted, in my experience, I quoted already 20 or 30 bridges around the world. The cost of the instrumentation is not more than 0.5, 0.7 million. And it's already a huge cost. We are not famous to be the cheaper in the market. even if we upgraded now with a good, cheaper solution. But the overall cost of the system, giving also the installation, which is a problem, the consultancy, the electrical connector, and so on, could be 2-3 million. That is much more less than the money eventually spent for the intervention. So, and this gives you at least an upgrade of the 30%. So you're saving money and you're extending the lifetime of your bridge. This is usually how I answer to the customer when they want to spend money in this solution. So now we have like a comparison why we should monitor bridge. Firstly, the traditional procedure are periodic, not continuous. You are doing picture of the bridge, which are far away, like months, even years between each other, while with the structural monitoring, you can do a continuously structural assessment. They are primarily visual-based, even if with the normal AI algorithm, you can do easily a detection of a failure just looking at the picture. They are still visual-based, not data-driven. And I explained, I think, pretty clearly, is approach much more reactive rather than predictive. And you are still missing an information. What happens in terms of traffic loads? This is why I brought to you the wake in motion. So, at KISTLER, I told you in traffic solution, we developed 2 different technologies. Wake in motion, here is like, I can tell you, is that basically that piece. And I can pass to some of you. Yeah. Thank you. Thank you so much. So wake in motion sensor are pressure sensor. There is a quick video and clip when you can see how they are consisting of. But basically, they are located in the asphalt, in the approach of the bridge, and in a sort of gate. Every car that passes on it is detected, and we can assume traffic statistics, so which type of car, the weight, the speed, the axle load. All this information you can monitor day by day, and you can understand the train day and night and month to month. You are keeping into account in your equation for understanding the structural condition of the bridge, the load. Something that is always missed. And, sorry. So, the other hand, we have the structural health monitor. We'll talk it about later. So, but you can ask why it's important to monitor truck or traffic. Because unfortunately, as I told you, the traffic load, the overloading is one of the most important causes for bridge collapse, especially in Asia, but as well as in US. Here in Switzerland, I didn't see those trucks, but if you pass in New York or even, I would say randomly in US, they are not trucks, they are dinosaurs. They are enormous. They are really enormous. Sometimes the wheel is even higher than me and say, look, now I understand why we do this job. Because a lot of those bridges have not been designed to resist this load. And this is a really important case. To analyze more on scientific wise, there is an exemplified estimation based on Miner's rule, which tell you very important thing, because basically the fatigue is cumulative. This is what it means. You have 3 scenarios. The first one, you have all legal trucks. Let's assume that the limit is 70 tons, okay? So all the trucks are legally passing on it. The bridge service life is 75 years. What happens if I overload the 20%, so I increase like 90, and it's still nothing, because I have also sometimes saw in the graphs 200 tons. So we are still like in the normal situation. By the 30%, the service life decreased to 60 years. In the worst scenario, where all the trucks are just overloaded 30%, the life is the half. So this means that the bridge is affected by a real big problem. How we tackle this problem in KISTLER? Here there is a quick movie about the wake in motion, just to give you a glimpse of what is. Basically, every linear sensor is consisting inside for small quartz disk. So the car has much more than 30, 40 contact points. It's perfectly embedded in the asphalt without doing any step. And especially for a road designing system, the truck, unfortunately for them, cannot pass it without escaping. And you can detect all this information, which are very important to understand the traffic trends. And you can do even direct enforcement. We are one of the few technology provider that can do the direct enforcement. Means that if the trucks pass in that specific gate and is not allowed, we can do the fine directly on it. So obviously we need a plate recognition by a visual-based camera, but the data is very, very precise, around 1% of error, and we can really tackle this problem in a pragmatical way. Here is what we obtain, all the condition, all the parameters, but where we applied. I came several times in US, my last 2 years, because we had a really good case study in New York. I don't know if you know how it's designed at Manhattan. Basically, it's a island. We have different connection, likely by one of the biggest and most famous bridges, so Manhattan, George Washington, Williamsburg Bridge, Brooklyn. But we have also, coming from Queens to Brooklyn, a triple cantilever, which is very, very old. And the New York City DOT approached us telling, look, we would like to do structural monitoring, but it's useful because we know that the bridge is degrading. So how you can keep the bridge open? I say, let's put wake in motion. So we put wake in motion in both westbound and northbound. And just to give you a couple of numbers, New York City is a really huge city and is affected by a really high number of trucks. Here pass much more than 130,000 cars per day. And just overweight are more or less 30,000 per day. So with the direct enforcement technique, the New York City DOT applied the first case of direct citation. So just for this bridge, every truck that's passing on it and is not allowed for technically for a limit of weight is fined. The total cost of fine for each truck is around $600, and this is the first step. Because if the limit if your weight is much more above than the limit, the increments of the price of the fine is not anymore linear, is exponential. So in terms of economic, this was a really good result of return of investment, because despite the cost of the system was pretty expensive, they get the money back in a couple of months. And this overall and allowed to have a 60% of decline of the overweight trucks, keeping the bridge open. Please.
How long does it take to install it, and how much is that process?
Good question. It depends how much is big the system, but usually we keep the traffic close for not much more than 8 hours. We work during the night, not me personally. But imagine that a bridge like this have 3 lanes. We install 2 sensors per lane, 4, 5, 6 hours, not much more. It's very easy because you need to do a pocket in the asphalt, like 3 or 4 centimeters. You can install, glue it, and cure. And it works immediately because the factor acceptance test and troubleshooting is very fast. Anything else? Yeah?
What is the lifetime of those sensors?
I would say more than 10 years. After 5 years, they need a calibration. So this means that we pass with weighted truck, and we understand if the answer in terms of structural response is still the same after 5 years. They're calibrated, and they can be to stay there since other 5 years. The technology accuracy depends, because there are different weight in motion. We have the quartz with the quartz inside. This piece is produced in Winterthur, and it's not Chinese, it's still Swiss made. And it gives you the accuracy, the reliability, and also the performance. You can use weight in motion with strain gauge. We can use weight in motion with fiber optics. So there are different technologies. These one are the most stable, even the most expensive. Any other question? No. So I talk about weight in motion. Now let's move to structural monitoring, which actually is my topic. And yes, since I joined the company, I say, okay, we are leader in acceleration sensor, but unfortunately, from a structural monitoring point of view, in the bridge, we cannot tackle the problem just looking with OMA, as Professor Tazzi for sure will talk about it. We need to integrate different parameters, so strain, temperature, displacements, inclination, and also other sensors like humidity, load cell. So in the new digital SIHM measuring chain, you have all this system produced by us and connected with just one simple cable to provide the power assumption and transmission of the signal. This gives you a good full overview because in the previous one, or generally, there are the analog system. You have each sensor connected with a cable to the DAQ, much more channels, much more cables. But here in every small box, there is the microchip for the MEMS, so for the acceleration sensor, or for the analog quantity, you have a very miniaturized DAQ. This reduces cost, and this reduces especially installation problem, because when the customer understand the technology and the value, the second pain after the cost is the installation, because it's much more demanding. In that case, the bridge I will show you, it needs maybe weeks to fully equipped. It's not much easier like... But what we need to do with structural health monitoring, I will not go very deeper because I know that there is a full course dedicated for it, but I will give you just a quick view on the process. And you can correlate basically the formula that you studied and I studied also, first of all, Fourier transform, and you will see how the process. So this is one of my most enjoyable, or I would say interesting aspects. When I receive a bridge layout, I need to define where to locate the sensor. So I understand which are the customer needs, the story of the bridge, and I try also to optimize because I would like to put sensor everywhere, but the budget at a point is limited. We are engineers, so we need to optimize. Usually, I will just give you a quick hint for accelerometers, because otherwise for strengths it will be so much long. So for acceleration sensor, the first aim is to understand the vibration mode. So you need to detect for natural frequency, damping, and mode shape. You locate the sensor mostly not where the function could be zero, otherwise you will not get any record. So, for example, for detecting like earthquake, you locate close to the basement. To understand the rotation of the pillar, you collect to the hinge, and mostly on the deck. After, you need to filter the signal, because you pass from a raw data to a digitalized one. In that case, you need to collect real information. And you need to apply filtering dedicated and data synchronization, because every sensor needs to speak each other with the same time reference. Otherwise, if you don't have synchronization, you cannot have a real good mood shape. These information that you gained are in the time domain, which is very important, very useful, but is not very easy to detect. For this case, you pass from time domain to frequency domain using, for example, the Fourier transform. In that case, with the frequency domain, in terms of practical wise, it's much more easy to detect the peak. And you can perform a mode analysis. So each peak is correlated to the mode, and the mode is correlated to a mode shape. It's, as I said before, if you can monitor, the structural monitoring means that you are comparing picture number 1 with picture number 2, picture number 3 over the time. If there is a degradation phenomena which is correlated to the stiffness, you will see by the decreasing of the stiffness and from the frequency itself. Any question? Obviously, these data, which are experimental, can be useful for another purposes. So model updating, you can calibrate model that you can do based on model of experience base, and you can update with the real numbers and try to match. The final aim, as it very intuitive, is to do damage detection, because I told you that the frequency is strictly related to the stiffness, and you can understand which is the degradation phenomena that is occurring on the bridge. And the last but not the least step is to do life estimation, because with data-driven approach, you can understand how much the damage will occur in the bridge and how much long will be extended the life. Any questions so far? Because it will be a quiz at the end of the lesson. Joking. Yes?
Most of this automatically done? I'm assuming if you're doing this continuously, a lot of different bridges doing this manually.
No, what do you mean, in terms of analytics or in terms?
In terms of the analytics, constant damage.
Yes, I would say there are two different approaches. With wireless system, our aim is to acquire continuously and ideally analyzing continuously. Guidelines, especially those one for masonry structure and after the consideration will be transferred in bridge monitoring, you need to acquire the signal not less than 40 minutes to have a statistical robustness. So you can do even small window like 10 minutes 4 times, but it's not the same like one for long, 40 minutes long. For the analysis itself, there are different algorithms. I would say that the approach is like a system that is sleeping. So it's continuous acquiring, continuously analyzing. You define statistically some trigger. When, for example, there is a threshold overpassed by acceleration signal or rotation. And in that case, the system goes deeper to see homogeneously what is happening on the bridge. So it continues analyze, but you need to define some specific trends or specific triggers. Otherwise, it will be too much consuming in terms of cost and data. So last chapter, I present you the both technology. Now, especially for this is a reason why we are here today, we are cooperating with one of your colleagues, Marina. I don't know if you know her. It's from maybe for the last year. We are doing a master thesis on this topic. So she is very active in trying to resolve this problem. And this was one of my missions when I joined the company, because having two technology, we try KISTLER we have a vision and we want to integrate it. How? From an engineering point of view, we have a problem, which is action, in this case traffic load, versus resistance. The resistance is mainly consisted by structural layout, geometry, material, design load. So this is the engineering problem. The best practice since now, unfortunately, in the last 50 years, to define both parameters, so both components, is for the traffic load, we have designing codes which are obsolete and they are not accurate because they are not keeping into account the current traffic load. And for resistance, you have modeling, you have inspection, which they keep still inside a good level of uncertainties. So being expert on measure how we can resolve this problem, we propose to measure both parameters. So actions from traffic load point of view are measured with the wake in motion because you have gross dead vehicle, axle load, and speed. For structural monitoring, with this overview of sensor, you can having a picture of the resistance due to the recording of the sensor. So what you obtain is a ratio that gives you the site-specific bridge reliability, because hopefully if the action are less than the capacity, the bridge is still standing on. What we don't want to have is the action are above the resistance. And this ratio is calculated day by day continuously, not just once in 1 day. Where we apply this methodology, I have several cases. Here I reported just the main 5 ones for type of bridge. I will talk to you later about Washington Bridge in Rhode Island, which was my first bridge that I started to monitor. I think that all of you know the Çanakkale Bridge in Turkey is the longest suspension bridge since the Italian government will know the Messina Strait Bridge. I think that will last several years. And here we have wake in motion. Imagine that the authorities in this case have some big concerning about, even if the bridge was brand new, also in this case there were some designing deficiency regarding the traffic. So looking at the normal or the correct number of traffic load, they designed again the strength of the cables. So even if the bridge sometimes is new and is one of the most advanced, it needs 20 years to be built, could have also some problem. The Chinese bridge is the 4th longest stay-cable bridge in the world, this Sutong River Bridge, and in this case, as in many others of this type, the problem is related to wind. The bridge was affected by a typhoon in 2008, and the University of Nanjing, Tech University, used our accelerometers, so almost 20 years ago, to monitor the bridge in that condition and calibrate again the tensile strength of the stay cables. After, we have two bridges in Italy. One is a multi-span reinforced concrete bridge, Clarea Viaduct, and also an arched bridge in Italy, which is very, very old. So now I will talk about Washington Bridge. So this bridge was very famous. It could be, for some reason, very comparable to Morandi Bridge. Obviously that we are very far from US, we don't read the newspaper, but luckily I was reading a couple of news and I saw that Rhode Island has a big concern about this bridge. Why? Because they do the normal approach, go on the bridge, do site inspection, everything is okay, let's pass on the other bridge. For such a coincidence, there were a couple of fishermen, they were passing down the bridge with a boat, they do some picture in the pier caps, they saw cracks big like this, and they say, okay, now we want to know why this bridge is still standing on without sensor. So Rhode Island contacted us. Here I have a quick movie I will send later. And basically this bridge has been evaluated as very critical. And as you can see in the picture, this span has been demolished. So the first concern of the owner was how the demolition work could affect the remaining span during the vibration. We are talking about 400 meters of bridge, it's not an easy play. And the second one is intuitive to say what we can do with the previous traffic. They cannot fly, they need to pass in the remaining one. This bridge was 4 lanes, now it's 6 lanes. Roughly estimation 50% or more of traffic, and also overweight truck. Because this bridge is a connection in the I-95, which is one of the biggest highways in US. The bridge is located in Rhode Island, I would say a little bit more north than Boston, and this lane connects all the East Coast. Here I reported a quick movie.
A new monitoring system that NBC 10 was first to report is now collecting data on the existing Washington Bridge. It's there to catch any potential issues early, and RIDOT says so far so good. Good evening, I'm Patrice Wood.
I'm Gene Valicenti. NBC 10's Gabrielle Caracciolo has an exclusive follow-up on the numbers coming in. Gabrielle?
Gene, Patrice, if you've driven over the Washington Bridge late at night in recent months, you've likely seen some lane closures. That was because of installation work on this structural health monitoring system. So charts like this are now showing about a week's worth of data at a time from the system. And RIDOT engineers say that some movement here is normal. They just don't want to see anything spike up to these red lines.
200 sensors across 14 spans of the Washington Bridge are now monitoring the critical piece of infrastructure at all times.
It measures vibration, movement, and in strain, which is like contraction or expansion.
Robert Ronchio is RIDOT's chief.
Finger on the pulse
Chief
of
engineer.
the bridge. We use that information to detect and address any potential issues very early on before they become a problem.
Yeah, I think that is done. So what we can extract from this important interview? We use the information from the monitoring system to address any issue very early on before they become a problem. So what I tried to explain you before with the predictive approach, here was the perfect example. We defined, as he said, the 200 sensor for structural monitoring for measure acceleration, tilt, and strain gauge of lower than 14 span, and is the biggest installation of wake in motion because we have much more than 40 sensors on both bound. And it's a gate, so every truck that's passing on it is not possible to not detect. Here some hints about the installation. As you can understand, sometimes there is a river, sometimes there is not a river, and this installation has been done also in winter, which for my colleagues was very challenging, because imagine to screw every box with the gloves was a nightmare. Luckily, my task was just to design the system and after give to them. So we have also the software, and this is the part that I want to show you now. How you can handle, basically, Rhode Island has the access on the dashboard and can give you a quick hint to look deeper at each span. So from span 1 to span 14, having a synoptic view of the system installation which I designed, and having a location of each sensor, and be connected each sensor with the related graph. You have, as Ronchio said, acceleration data, strain gauge, altimeters, and since there is no the threshold passed for some value, everything is okay. If you want to have a deeper look into the data, You can go in a high-resolution way. Here, for example, acceleration data. This was a very, very important during the demolition phase, rather than a normal behavior of the bridge, because we expect that there is a truck passing on it, it would be a spike. The most important point was to understand 10 hours of demolition, how could effectively affect the remaining bridge. So this is the structural health monitoring. If you want to pass on the waking motion, there is this window. And here you can see the trend up and down, is obviously day and night. But there is also the trend due by weekdays, working days, and weekend days. I will give a couple of questions now. So obviously you can understand which one is the biggest or the most common traffic category, the cars. The green one is related to the overweight trucks. It is still consistent for every day. And you can diagram this data in function of the plus vehicle weight, the mean gross. Marina is working on it and is getting good insight. So I have a question for you now. Which scenario is much more problematic for you? Respect the early morning or the late night? So which scenario in terms of traffic load is much more severe to the condition of the bridge? Try to think. Intuitively. Why?
For like rush hour time, there's much more traffic on the bridge.
Okay, this is a good answer. Are you sure? I mean, anything else? Someone of you? Just put idea. There is not an incorrect question. Spoiler. Early in the morning? This is a good point. We have also temperature sensor to correlate, but it's not strictly related. So in the early morning, as you both said, you have the rush hours. This means that there are so many cars really close to each other that can act as a big, huge static load on the bridge, okay? Because all the people are moving to go to work. But why the late night is not a good time for you? Imagine that there is no traffic. There are the truck driver, they can run even faster. And imagine a 200 tons truck passing 70 or 80 or 100 miles per hour on the joints. It's a huge strike of a hammer instead of a traffic normal condition. But obviously, this is a point that you cannot imagine if you don't look into the data. Even traffic loads at some point is like intuitive object because we know trucks, we know cars, okay, maybe in the early morning, maybe the people are going back at the work at 5 p.m. What about the night? The night is also a problem. So the good point is if you handle the data, you can get decision. And yes, this is the last tool that we defined. As in the Brooklyn Queen Expressway, imagine that the bridge has 5-6 lanes. Intuitively, if it's a bin-type bridge, the external ones, so 1, 2, 3, 5, 6, the 1 and the number 6 are the most affected because they are not supported, okay? But what you can do, you can understand how the load is much more affecting those lanes and eventually close it, partially, just in some hours of the day or in some days, keeping the bridge open. Any question?
Just to say that it's good, we don't have much more time.
In finish, this is the conclusion. So, indeed, okay, so summary and conclusion. I will pass from here, yes. So we understood which is the problem, that millions of bridges are affected by the end of their lifetime, and among the biggest causes, one of the most important roles, unfortunately, is increased traffic. In KISTLER, we want to measure both parameters and give a really good answer to this problem. But one question for you could be, why not every bridge is monitored? Which is the biggest point? You could say cost. No. Unfortunately, what we are working on it, especially KISTLER, but also cooperating with university as ATH, Professor at sea, we need to reduce the gap between the data, the measurement, and the information. This is given by continuous working on it, starting maybe from master thesis, that could be developed in PhD thesis, that could be developed in important tool, and after give you an extensive and exhaustive report to the customer. The path is very long, but we hope that also with your help, we can go in this direction. So thanks for the attention. Perfect on time.